So in this video we want to introduce the cylindrical coordinate system. And the idea is the cylindrical coordinate system is really just an extension of the polar coordinate system that we saw in a previous video. So remember when we did polar coordinates, we were working in the XY plane, and when we had a point, we drew the line segment from that point to the origin. So we really had a directed line segment. We could think of this as a vector if we wanted to. And then we had an angle theta that we formed with the XY, with the positive x-axis. And we had a radius, which was just the length of the line segment from the origin to the point we were interested in representing. And really with the cylindrical coordinate system, all we're doing is then pulling out a z-axis and adding in a third coordinate, z. And we just let z represent itself. So nothing fancy about z. Z is just going to be the directed distance from the point in the xy plane up to the point P that you're trying to represent. So cylindrical coordinate systems, you have r and theta, which are just the r and theta from polar coordinate system. And then we add in that z coordinate, which is the directed distance or directed vertical distance from the xy plane, or from the point r theta 0 right here. This is the point r, radius theta, and then 0 is the point in the xy plane. So pretty straightforward. Some spins that you can get on this that you need to be aware of. So if we think about this, how we label axes is it's kind of arbitrary, I guess, in a sense. So we could just as easily have this axis as the y-axis and this axis as the z-axis. And if we did that, then theta would still be the angle that we make with the positive x-axis, and the radius would still be the length of the line segment. We would be pulling out a y-axis from that. So there's a sense in which this could be r theta y, where r and theta are generating a position in the xz plane, and then y would be the directed distance from the xz plane out to the point. And we could just as easily have the vertical axis represented as the x-axis, and we can make this the y-axis. And then if we did that, we'd have r and theta. So we'd have y and z. So theta would be the angle that we make with the positive y-axis. R would still be the length of the line segment. And then here, instead of z, we would have x. So when you define the cylindrical coordinate system, you typically define it in terms of r, theta, and z. But what we want to understand is that this could be r, theta, and y, or r, theta, and x, depending on whether the cylinder is extruding with respect to the xy, the yz, or the xz planes. So because this is just an extension of the polar coordinate system into three-dimensional space, the relationships we had for polar coordinates are still going to hold, and all we do is add in the third relationship that z is itself. Z is equal to z. So in the xy plane, we got some relationships coming to us from trigonometry. If this angle theta is made with the positive x-axis, we know that by the Pythagorean theorem that the x-coordinate squared plus the y-coordinate squared is going to equal the lengths, r squared, the length of the line segment squared. We know that the tangent of theta by definition is going to be the y-coordinate divided by the x-coordinate. And then because we're just extruding that z-axis, we just let z equal z. We don't have to do anything fancy with the z-coordinate. So that's all that changes when we move from polar coordinates to cylindrical coordinates. Again, because how we label the axes is arbitrary. For example, this could be the y-axis and this could be the z-axis. And if we did that, then we have to make tweaks to these relationships. So if I change this to x, z, and y, then I would get r squared equals x squared plus, we would get z squared. We would get tangent of theta has to be, if this is the z-axis, then it's going to be, these are going to be x, z coordinates. So the tangent would be z over x. And then instead of saying z equals z, we would just say y equals y. And similarly, if we decided that this was the x-axis, then this axis would be the y-axis, so we would change this to y. This would be the ordered pair yz, and then we would have to change our relationships here to adjust for that. We would get r squared equals y squared plus z squared. The tangent of theta would be equal to z over y, and we would get that x equals x. And we would need to make the adjustments here as well. We might get y equals r cosine theta, z equals r sine theta, depending on how we're orienting our cylinder. Are we orienting the cylinder with respect to the xy, the xz, or the yz planes? So the standard method for defining these is in terms of the z-axis being the axis that you're extruding the cylinder with respect to, but you need to make the obvious tweaks to the formulas if you're extruding your cylinder with respect to or parallel to the y or x axes. If you extrude the cylinder with respect to the x-axis, you'll get x equals x, and you need to tweak these. If you extrude your cylinder parallel to the y-axis, then you're going to get y equals y, and you'll need to tweak these formulas to take that into account.